Welcome to Bedtime Science. Did you know that your brain can quietly rewrite the habits you thought were permanent? Not through force, but by gently changing how you see the world. Most people believe breaking a bad habit requires enormous willpower, but neuroscience tells a different story. The brain can simply outgrow old patterns, the way a river slowly carves a new path through stone. Tonight we explore how the nervous system learns to let go. In the next moments, we will gently move through how habits get built into the physical structure of your brain and why they feel so impossible to shake. How a Harvard-trained psychiatrist realized that fighting a tendency matters far less than quietly changing it. How your tongue was born rejecting bitter flavors, yet millions of people now crave black coffee each morning. How the attachment patterns you formed as an infant get recycled into your adult relationships, and why simply knowing about them begins to shift them. And how your DNA provides the blueprint while your lived experience writes the actual code. Before we begin, if you find comfort here tonight, consider subscribing to join our quiet community. And if you are still awake, you can leave a soft comment about what topic we should explore next. Now let's begin. Your brain is a creature of efficiency. It doesn't want to think about everything all the time. That would cost too much energy. So it automates. And the way it automates is through repetition, the same neural pathways firing over and over until they become smooth, fast, and nearly invisible to your conscious mind. This is how habits form, not in a single dramatic moment, through thousands of quiet repetitions. Each time a neuron fires and activates a neighboring neuron, the connection between them grows a little stronger. The synapse, that tiny gap between two nerve cells, becomes more responsive, quicker to transmit, easier to trigger the next time. Neuroscientists have a shorthand for this. Neurons that fire together wire together. Think of it like a path through a dense forest. The first time you walk through the undergrowth, you have to push branches aside and step over roots. Your feet crush the tall grass. Everything is slow and deliberate, but walk that same route every day for a year. The grass dies back. The soil compacts under your shoes. A visible trail appears. After 5 years, it looks like the path was always there, as though someone built it on purpose. Your brain does exactly the same thing with behavior. The first time you reach for your phone when you feel anxious, the neural pathway is faint, barely there. But after 1,000 repetitions, that pathway has become a highway. Smooth, automatic, fast. Deep beneath the outer folds of the cortex, a cluster of structures called the basal ganglia manages this process of automation. The basal ganglia sits wrapped around the thalamus like a set of nested shells, and its job is to take behaviors that once demanded your full attention and package them into routines that run without any conscious oversight at all. This is genuinely useful. When you first learned to tie your shoes, every loop and pull demanded your complete concentration. Your prefrontal cortex, the thinking and planning region behind your forehead, had to supervise each step. But after enough practice, the basal ganglia took over. Now you tie your shoes while thinking about something else entirely. The behavior runs on its own. Here's the thing. The same process applies to emotional habits. The first time you responded to criticism with defensiveness, your brain was making a conscious choice. But after years of the same reaction, the basal ganglia packaged that response into an automated routine. Now defensiveness fires before you even realize what's happening. The behavior you once chose has become a behavior that chooses you. And this matters because the brain prefers efficiency over accuracy. It would rather run a fast, automated program, even one that's slightly wrong, even one that doesn't serve you anymore, than spend the metabolic energy required for careful, conscious evaluation every single time a situation arises. Your habits aren't necessarily the best responses to your life. They're the most practiced ones. That's why habits feel permanent. They are physically encoded in your neural architecture. The synapses are strong. The pathway is deep. The basal ganglia runs the program without asking your permission. But physically encoded doesn't mean physically fixed. And that distinction is where everything changes. Consider the difference between a behavior you actively choose and one that runs automatically. When you're choosing, the prefrontal cortex is engaged. You're weighing options, considering consequences, making a deliberate decision. But when a habit fires, it bypasses all of that. The basal ganglia detects a familiar cue, retrieves the stored routine, and executes it before the prefrontal cortex even gets consulted. This is why you sometimes catch yourself mid-habit, already 3 bites into the snack or already scrolling through your phone, and you think, wait, I didn't decide to do this. You're right, you didn't. The basal ganglia decided for you. Or more accurately, it ran a program that was written months or years ago, when the circumstances were different and the behavior made more sense. The stored routine doesn't update itself. It doesn't check whether the old behavior still fits your current life. It just runs, like an old program on a computer that nobody bothered to uninstall. But the brain is not a computer, and this is where the science gets interesting. Because unlike software, neural pathways are alive. They strengthen when used, and they weaken when neglected. Every synapse in your brain exists in a state of quiet competition with every other synapse for metabolic resources, for space, for survival. The connections you reinforce get stronger. The ones you abandon get weaker. Not overnight, not in a week, but steadily over months, like a garden path that slowly disappears when no one walks it anymore. Habits feel like concrete. They're actually more like packed earth. These first observations describe how patterns get built into the brain. The next group looks at why the most popular approach to breaking them, raw willpower, so often fails, and what actually works instead. Dr. Alok Kanojia is a Harvard-trained psychiatrist who co-founded Healthy Gamer and specializes in modern mental health. During a conversation on the Huberman Lab podcast, he asked a question that reframes the whole science of behavioral change. He said, everyone's focused on changing behavior. Everyone's focused on increasing willpower to overcome this tendency. And it's like, why not just change the tendency? Sounds too simple, almost suspiciously simple. But sit with it for a moment. Most approaches to breaking bad habits assume the habit is a fixed force, and you need to generate an equal or greater opposing force, willpower, to overcome it. Dr. Kanojia suggests something completely different. Don't fight the force. Change it, dissolve it, make it irrelevant. To understand why this matters so much, consider what willpower actually is at the biological level. Willpower lives primarily in the prefrontal cortex, the region that handles impulse control, long-term planning, and conscious decision-making. This region burns glucose at a high rate. It fatigues. It's expensive to operate. Dr. Kanojia identifies 4 major drains on this system: suppressing emotions, repressing emotions, restraining desires, and overriding habits. When all 4 are running at once, and for most people navigating a typical day, the prefrontal cortex runs out of fuel. That's burnout. That's the Wednesday evening collapse when you said you wouldn't eat the chips, but you ate the chips anyway. Look, willpower is only necessary when it has to override something, when you're fighting an urge, pushing back against an impulse, white-knuckling through a craving. But what if the urge itself dissolved? What if the impulse simply stopped arising? Dr. Kanojia puts it this way: willpower is necessary when you are trying to not be narcissistic. It is not necessary when you are no longer narcissistic. That one sentence captures the entire difference between suppressing a pattern and actually dissolving it, between gritting your teeth through every day and waking up one morning to find the old craving simply isn't there anymore. Your brain runs two separate behavioral control systems, and the cost difference between them explains everything about why willpower fails. The prefrontal cortex is expensive, fragile, and easy to deplete. Even one night of poor rest can reduce its activity by 20 to 30%. Chronic stress shifts behavioral control away from the prefrontal cortex and toward the basal ganglia through elevated cortisol. Think about that. Stress literally hands the controls to your automated habits. The basal ganglia, on the other hand, is cheap. Automated routines stored their run with minimal metabolic cost. They don't burn through glucose reserves. They don't need the prefrontal cortex to supervise. They don't tire out. So when you try to change a habit through sheer willpower, you're asking an expensive, depleting, fragile system to continuously override a cheap, automated, persistent one. The prefrontal cortex must win every single encounter. The basal ganglia only needs to win once, when you're tired, stressed, distracted, or hungry, to reinstate the old pattern. This is why New Year's resolutions collapse by February. Not because people lack character, because the architecture is mismatched. Dr. Kanojia says it directly. If you are using willpower every single day to restrain your desires, restrain your ambitions, restrain your habits, and restrain your emotions, you will burn out. The real question isn't how to build a bigger willpower battery. It's how to stop needing one. Drawing from Vedic psychology, Dr. Kanojia describes something called samskaras, accumulated emotional impressions that shape how you perceive and respond to the world. A samskara functions like emotional scar tissue. It formed in response to a real experience. It was protective once, but over time it became rigid, triggering reactions that no longer fit the situation you're actually in. Here's what makes samskaras tricky. They can't be dissolved by telling yourself something different. As Dr. Kanojia explains, telling yourself is very surface-level mental activity. That's not how change happens. Instead, samskaras require experiential processing. Practices like meditation, yoga nidra, or deep psychotherapy that reach the pattern at a level below words and conscious thought. This connects to something Dr. Kanojia observed about perception and motivation. He noticed that changing a phone's display to grayscale reduces average daily usage by 37 minutes. No willpower involved, no discipline, no white-knuckling. The perceptual input changed, and the behavior followed automatically. 37 minutes, just from removing color. That is the template for lasting behavioral change. Don't try to overpower the old behavior. Change the perception that feeds it, and the motivation reorganizes on its own. Dr. Kanojia describes this beautifully. As you practice seeing the world as it is and separating out all of the crap that your mind attaches to it, motivation will naturally rise, and you don't need discipline. When psychotherapy genuinely works, not just coping, but real change, it doesn't merely alter what someone does. It alters who someone is. Their natural thoughts begin to shift. The way they see the world begins to shift. Their instinctive orientation toward experience rewrites itself. And when that happens, willpower becomes beside the point. There's nothing left to override. There's a quiet moment in genuine change that rarely gets talked about. It's the moment when the old pattern simply stops showing up. Not fought, not controlled, not suppressed with effort, just absent, like a forest path that no one has walked in years. The grass grew back without anyone noticing. Roots stretched across the bare soil. Leaves fell and stayed. And one day you look for the old trail and realize it's gone. That moment doesn't feel dramatic. It feels like nothing happened. And that's exactly how you know the tendency itself has changed. These observations about willpower and perception lead to a natural question. If deeply ingrained psychological patterns can shift, what about patterns that seem even more fundamental? What about the responses written into your body before you ever took your first breath? Dr. Charles Zuker is a professor of biochemistry, molecular biophysics, and neuroscience at Columbia University. He has spent over 30 years mapping the molecular and neural architecture of taste. His research provides what might be the most vivid biological proof that hardwired does not mean permanent. The taste system is ancient. It's one of the oldest sensory systems in the human body, and it is innately organized. From birth, before any learning has occurred, before any experience with food, humans are attracted to sweet and repelled by bitter. These aren't preferences you develop over time. They are behavioral programs you are born carrying. When bitter receptors activate on your tongue, a whole cascade fires automatically. The mouth closes, the tongue retracts, the face contorts, gagging begins. When sweet receptors activate, the opposite happens. Licking increases, the body leans forward, the organism seeks more. Dr. Zuker's lab demonstrated something remarkable about these responses. They work even when the tongue is completely bypassed. When researchers directly activated the bitter-responsive brain regions in mice, without any bitter substance touching the tongue at all, the full behavioral program executed. The mice gagged and recoiled while drinking plain water. The brain ran the rejection program based on the neural signal alone. The 5 basic tastes work like piano keys. Each one activates a separate neural cord that triggers specific behavioral instructions. Sweet means energy, approach. Bitter means potential poison, reject. Sour, salty, umami. Each one carries its own built-in command, hardwired before birth. And yet, Dr. Zuker is emphatic about a single point. He says, predetermined hardwire doesn't mean that it's not modulated by learning or experience. It only means that you are born liking sweet and disliking bitter. Consider coffee. Your tongue is born to reject it. The bitter compounds in coffee activate the same receptors that would fire for plant toxins, the same ones that warned our ancestors away from poisonous berries on the forest floor millions of years ago. An infant tasting coffee for the first time would gag and turn away. The hardwired program executing exactly as designed. But you probably had coffee this morning, or yesterday, or you're planning to have it tomorrow. So what happened? Dr. Zuker explains, we learn to love coffee because it carries an associated gain to the system. Caffeine activates neurotransmitter systems that produce alertness, energy, a mild boost in focus and mood. That positive outcome creates a new association layered on top of the original rejection. But here's what matters. The bitter signal doesn't vanish. Your tongue still detects bitterness. The bitter receptors still fire every single time, but the brain has learned to associate that signal with a downstream positive outcome. And the positive association overpowers the hardwired aversion, not by erasing it, by building something new on top of it. The old circuit is still there. A new one has been constructed alongside it, and the new one wins because it carries a stronger prediction of reward. The reverse works the same way, but in a single shot. Conditioned taste aversion, when a food gets paired with nausea even once, can permanently reverse a previously attractive flavor. If you ate strawberry ice cream and then got violently ill, your brain might flip the emotional value of strawberry from positive to negative in one experience, even if the illness had nothing to do with the ice cream. One trial, one reversal. Dr. Zuker's lab showed that the identity of a taste and its emotional value are processed in different brain regions. The taste cortex handles identification. What are you tasting? The amygdala assigns the emotion. Is this good or bad? And because these two systems are separate, they can be changed independently. You can keep recognizing a flavor while completely reversing how you feel about it. There's a detail from this research worth sitting with for a moment. Taste receptor cells live only 10 to 15 days. Then they die. They're replaced by new cells. Every 2 weeks, the cells on your tongue that detect flavor are entirely new. And each time a new cell is born, it must connect to the correct nerve fiber. Bitter cells to bitter nerves. Sweet cells to sweet nerves. Dr. Zuker's lab identified 2 molecular signals, semaphorin 3A for bitter and semaphorin 7A for sweet, that guide this reconnection. When those signals are disrupted in the lab, mice can no longer tell bitter from sweet. The wiring scrambles. So even the most hardwired sensory system in your body is rebuilt from the ground up every 14 days. The cells themselves are temporary. The wiring is continuously reconstructed over and over across your entire life. The system only appears permanent because it faithfully rebuilds itself according to the same molecular instructions each time. But those instructions can be modified by experience. If a sensory circuit shared with organisms hundreds of millions of years old can be rewritten by new associations, then the behavioral patterns you picked up last year, or 5 years ago, or in childhood, are not carved in stone. They're packed earth, and packed earth can be reshaped. The observations so far have looked at habits and taste, patterns shaped by experience and biology. The next group of quiet observations concerns something more intimate, the emotional patterns formed in the very first relationship of your life. In the 1960s, a developmental psychologist named Mary Ainsworth designed an experiment she called the strange situation. The setup was deliberately simple. A mother and her toddler enter an unfamiliar room. The mother leaves. A stranger enters. Then the mother comes back. Ainsworth wasn't measuring the child's distress. All children showed distress when the mother left. What she measured was the pattern of the child's response when the mother returned. And from those patterns, 4 distinct attachment styles emerged. Securely attached children were upset when the mother left but calmed quickly when she returned. They used her as a safe base, venturing out to explore, returning for reassurance, then exploring again. Anxious avoidant children showed little visible distress when the mother left and seemed to ignore her when she came back. But physiological measurements told a different story. Their heart rates were elevated. Their cortisol levels were high. They had learned to suppress their need for connection because expressing it hadn't been rewarded. Anxious, ambivalent children were intensely distressed by the separation and difficult to console when the mother returned. They clung and pushed away at the same time. They had learned that caregiving was inconsistent, sometimes available, sometimes not, and their nervous system stayed in a state of vigilant uncertainty. Disorganized children showed no coherent strategy at all. They might approach the mother while looking away. They might freeze mid-step. This pattern typically emerged when the caregiver was both the source of comfort and the source of fear. Here's why this matters for tonight. These four patterns formed before a child has language, before a child can reflect on their own behavior, predict adult romantic attachment with striking consistency. The neural circuits originally built for child-caregiver bonds get repurposed for romantic attachment in adulthood. The same autonomic responses, the same patterns of approach and avoidance, the same empathy circuits recycled from their original developmental context into adult love. Andrew Huberman described the autonomic nervous system as a seesaw with a hinge. The hinge represents your autonomic tone, how readily your system tips between alert and calm states. Child-caregiver interactions calibrate this hinge during the earliest years. Huberman references studies from World War II. When mothers remained calm during bombing raids and turned shelter visits into games, their children did not develop lasting stress responses. When mothers were visibly distressed, children's physiology remained elevated long after the danger had passed. The children's autonomic nervous systems mirrored their caregivers. So your attachment style isn't just a psychological label you read about in a magazine quiz. It's a physiological calibration, a setting in your autonomic nervous system that was tuned during the first years of your life and then carried into every relationship that followed. But here's the part that shifts everything. These templates can change over time. Huberman says this directly. He notes that the neural circuits for desire, love, and attachment are quite plastic, meaning they retain the capacity to be reshaped throughout adulthood. And one of the most striking findings in the research is about how that reshaping starts. One powerful way to shift attachment templates is purely by knowing they exist and understanding they're malleable. That's it, just knowing. Not fighting the pattern, not forcing yourself to behave differently, not white-knuckling through relationships, just seeing the pattern clearly, understanding where it came from, recognizing that it was a sensible adaptation to the environment you grew up in, and allowing your nervous system to update its predictions based on new information. This connects directly back to Dr. Kanojia's insight. Awareness of a pattern is the first step toward changing the perception that keeps it alive. You don't need to wrestle with your attachment style. You need to see it, and seeing it begins to dissolve it. Adults can and do migrate from insecure attachment toward secure attachment. This happens through new relationships, through therapy, through deliberate practice. Huberman describes this with a simple phrase: just a rewiring of nerve connections. Just a rewiring, as if the nervous system rearranges itself all the time. And honestly, it does, every day, every night. The observations so far have examined patterns shaped by experience, habits, taste preferences, attachment templates. But what about patterns written into your DNA before you were conceived? Can those change too? Dr. Catherine Page Harden is a professor of psychology at the University of Texas at Austin and director of the Developmental Behavior Genetics Lab. Her work addresses one of the most sensitive questions in modern science. How much do your genes determine your behavior? Her answer starts with a metaphor. It was developed in the 1940s by an embryologist named Conrad Waddington. Waddington pictured a ball sitting at the top of a hilly terrain with valleys and ridges. As the ball rolls downward, it gets channeled into particular grooves. Deeper channels represent more constrained developmental paths, outcomes that are difficult to deviate from. Shallow channels represent less constrained paths, outcomes that respond more easily to environmental influence. This is what Harden means by canalization. Genetic predispositions channel behavior. They create grooves, but the terrain itself isn't fixed. It's shaped by the ongoing interaction between your genes and your environment. And the ball can, under certain conditions, jump from one valley to another. Here's something counterintuitive from her research. Genetic influences on behavior actually become stronger with age, not because genes get louder over time, because of path dependence. Consider a child with a slight genetic nudge toward extroversion. That child joins a sports team, develops social skills, gets reinforced for sociability by peers and coaches, chooses more social environments as a teenager, and becomes increasingly extroverted through their 20s. The original nudge, which was small at age 5, has become a deep groove by age 25. Not because the genes changed, but because the child built environments that amplified the original tendency. Dr. Harden uses the Waddington image directly. She says you can picture a terrain that's kind of flat or undulating, and the ball has lots of movement across it as it goes down. But our educational system works nothing like that. We channel people into groups early and make it very hard for them to jump tracks once they're placed. But jumping tracks is biologically possible. One of Harden's most cited findings involves a family therapy intervention for adolescents at genetic risk for alcohol use disorder. Her team used a polygenic risk score, a single number combining thousands of DNA variants, to predict who would develop alcohol problems. And the score worked. It predicted outcomes reliably. Until the families received structured therapy. When parents were taught to monitor curfews and friend groups, the polygenic risk score stopped predicting alcohol use. The environment overrode the genetic channel. The groove was real, the predisposition was measurable, but the intervention moved the ball to a different valley. This parallels Dr. Zuker's taste research in a striking way. The predisposition is real, the biology is real, but it's modulated, sometimes completely overridden by experience. Your genes wrote the first draft, but you hold the pen for revisions. And the revisions don't require fighting your DNA. They require changing the environment, the conditions, through which your genetic tendencies unfold. DNA provides the architecture. Learning and conscious intervention provide the programming. And as one researcher described it, medicine and conscious intervention can now program cell behavior in a way that's much more directed than was ever conceivable before. The big leap isn't in changing genes themselves. It's in changing what those genes express under different conditions. These observations about genetics bring us to a question about mechanism. If patterns can change, whether they're habits, taste preferences, attachment templates, or genetic predispositions, what is the brain actually doing when it releases an old pattern? How does the physical process of letting go actually work? Part of the answer arrives every single night. Two professors of psychiatry at the University of Wisconsin-Madison, Giulio Tononi and Chiara Sirley, proposed what might be the most elegant explanation of why the brain needs nightly rest. They call it the synaptic homeostasis hypothesis. The idea goes like this. During the day, every experience you have strengthened synaptic connections. Every conversation, every observation, every emotional reaction, every decision adds weight to the neural network. Synapses get stronger. Connections multiply. By evening, the brain is saturated. Too many connections, all too strong, consuming too much energy. Then you close your eyes. During the deep, slow phases of nightly rest, the brain does something quiet and systematic. It proportionally weakens all synapses. Every connection gets dialed down by the same fraction. The connections that were strongest, the most meaningful learning from the day, survive this downscaling. They stay above the threshold of viability. But the weakest connections, noise, irrelevant associations, pathways you didn't use, drop below the threshold and are eliminated. Gone, pruned from the network. The molecular machinery behind this involves specific receptors called AMPA receptors. During waking hours, learning drives the insertion of these receptors into synaptic surfaces, making connections stronger. During deep rest, slow oscillations in the cortex, the brain cycling between firing and silence at frequencies below 1 Hz, trigger the removal of those same receptors. A 2024 study measured approximately a 40% decrease in one type of AMPA receptor at synapses during this process. 40% in a single night. The system has a beautiful self-limiting feature. As synaptic strength decreases, neurons become less synchronized. The slow oscillations diminish in amplitude. When synaptic weight returns to baseline, the waves can no longer drive further downscaling. The process terminates naturally. This explains why the deepest, most restorative brain waves are strongest at the start of the night and decline across the hours. There's a pruning threshold. Synapses that were already weak before you closed your eyes, those encoding patterns you haven't reinforced recently, get weakened further during this nightly downscaling. If they drop below a minimum strength, they're eliminated from the neural network entirely. Tononi and Sirley call this downselection. But here's what matters for unlearning. Not practicing an old habit is not passive. It's an active biological process. Each night that passes without reinforcing the old pattern makes that pattern's neural substrate weaker. The synapses that encode it receive no strengthening during the day. Then during the night, they're weakened further by the same proportional downscaling that affects every connection in your cortex. Given enough nights, the pathway drops below the pruning threshold. It is dismantled, synapse by synapse, night by night. The old habit doesn't just fade from awareness. Its physical infrastructure gets taken apart. The cells that once fired together in that pattern lose their strengthened connection. The automated routine stored in the basal ganglia loses the synaptic support that kept it running. A 2024 study confirmed that the deep, slow phase of rest, not the dreaming phase, is the primary driver of this synaptic renormalization. When researchers selectively prevented dreaming while preserving the deep slow wave phase, AMPA receptor levels remained normal. But when they prevented the deep phase entirely, synaptic receptor levels surged. The brain's cleanup crew had been locked out. Your brain runs this audit every night. It's running tonight after you finish listening. The patterns you reinforce today will be preserved. The patterns you didn't practice will be weakened. And given enough time, given enough nights of not reinforcing the old response, they'll be pruned away entirely. Like a gardener who doesn't need to pull every weed by hand. Some weeds, if you simply stop watering them, wither on their own. The observations so far have described what happens to synapses. But there's another layer to unlearning, one that operates not at the level of individual connections, but at the level of entire brain networks. And this layer concerns something you might not expect: stories. Your brain tells stories about who you are, constantly, without being asked. Deep inside your brain, a network of interconnected regions activates most strongly when you aren't focused on anything external. When you're daydreaming, remembering something from the past, imagining something in the future, thinking about yourself. This network is called the default mode network, and it includes the medial prefrontal cortex, the posterior cingulate cortex, the precuneus, and parts of the temporal lobe. The default mode network's most important job, at least for tonight's topic, is constructing your sense of self. Researchers call this the self-construction hypothesis. The idea is that this network continuously and dynamically builds your identity. It takes past experiences, reevaluates them, reinterprets them, and weaves them into an ongoing story about who you are and who you've always been. The medial prefrontal cortex sits at the center of this process. Brain imaging studies show it activates specifically during self-referential thought. When you think about your own traits, your own history, your own likely future, it processes what researchers call the narrative self, the ongoing autobiography you carry in your head. Here's where this connects to the science of unlearning. Negative behavioral patterns are sustained in part by the stories the default mode network tells. I'm an anxious person. I always mess this up. I can't help it. These feel like facts about yourself. They feel solid and permanent, but they're not observations. They're outputs. They're narratives constructed from selectively recalled memories and emotionally weighted interpretations. The default mode network picked certain memories, ignored others, assigned emotional weight according to old patterns, and assembled a story that feels true but is actually edited. Your brain doesn't passively receive the world, it actively constructs it. Your perception of who you are is not a photograph, it's a painting, and the default mode network holds the brush. When this network becomes overactive, it drives rumination, the repetitive, circular replay of negative self-stories. A 2025 study found that people with depression and social anxiety showed stronger default mode network activation during social comparisons. They weren't just thinking about themselves more often. They were telling themselves worse stories and finding it harder to disengage from those stories. But the default mode network responds to intervention. Meditation has been consistently associated with reduced activity in this network. A study in cognitive, affective, and behavioral neuroscience found that experienced meditators showed suppressed default mode network activation not only during practice, but also during regular cognitive tasks. The regions showing the strongest changes were the posterior cingulate and anterior cingulate cortex, precisely the core nodes of the self-narrative system. This isn't a temporary effect. Long-term meditation appears to remodel the network's baseline settings. The storytelling engine doesn't just get quieter when you sit down to meditate. It gets quieter in general. Consider what this means for changing patterns. When psychotherapy, meditation, or new experiences shift the inputs to the default mode network, the narrative itself revises. And when the narrative revises, the pattern it sustained loses its foundation. If you no longer tell yourself, "I'm an anxious person," the behaviors associated with that identity begin to loosen their grip. Not because you suppressed them with effort, because the story that held them in place was gently rewritten. The brain is a prediction machine. It doesn't wait for the world to happen and then react. It predicts what will happen and then checks whether the prediction was right. Your self-narrative is one of its most powerful predictions. I am the kind of person who fills in the blank before the situation even arises. Change the prediction, and the behavior follows naturally, like water finding a new low point. These observations about perception and self-narrative bring us to the brain's most fundamental teaching signal, the system that decides what feels rewarding, what feels neutral, and what feels like a disappointment. Dopamine neurons in the midbrain don't simply respond to rewards. They respond to the difference between what you expected and what you actually got. This signal is called the reward prediction error, and it is the brain's primary tool for learning what to repeat and what to stop doing. The system runs on a clean principle. When a reward arrives and it's better than expected, dopamine neurons fire above their baseline rate. That surge tags the behavior as worth repeating. When the reward matches the prediction exactly, dopamine neurons hold steady at baseline. Nothing to learn here, the brain says. Already figured this out. And when the reward is worse than expected or doesn't show up at all, dopamine neurons fire below baseline. That dip weakens the association. The brain begins to expect less from that behavior. This is how new habits get built. Early on, a new behavior produces an unexpected positive outcome. Dopamine fires a positive prediction error. The brain says, "That was better than expected, pay attention." Over time, with repetition, the dopamine signal migrates from the reward itself to the earliest cue that predicts the reward. This is why habits eventually get triggered by environmental cues: the smell of coffee, the sight of your phone, the sound of a notification, the feeling of boredom, rather than by conscious decision. And this same system explains how old habits can be weakened from the inside out. When you stop reinforcing an old pattern, when the expected reward no longer arrives, negative prediction errors accumulate. Each time the brain predicts a reward that doesn't come, dopamine dips below baseline. The synaptic connections encoding the old habit weaken slightly. Given enough repetitions of disappointed expectation, the pattern loses its neurochemical momentum. But there's a catch, and it's important to understand. The dopamine prediction error system has a built-in feature that makes change difficult. Any reward you receive automatically updates the prediction upward. Yesterday's unexpected pleasure becomes today's expected baseline. To generate the same dopamine surge, the same positive prediction error, the reward has to be bigger, or newer, or more intense. One researcher described it this way: the system doesn't just drive us toward rewards, it drives us toward ever-increasing rewards. That's the escalation problem, and it explains why willpower-based approaches to habit change struggle. They ask you to suppress a dopamine-driven desire without offering your brain an alternative signal. The old pattern continues generating expected rewards, even if that reward is just the relief of tension or the comfort of familiarity. The new, healthier pattern generates nothing. No positive prediction error, no dopamine surge, no signal that says this is worth repeating. The real approach isn't to fight the dopamine system. It's to give it something new to learn. When a new behavior produces genuinely unexpected positive outcomes, the prediction error fires. Dopamine tags the new behavior as worth repeating. Over weeks and months, the new association strengthens while the old one, deprived of its expected reward, weakens. You don't need willpower to sustain this in the long run. You need time, consistency, and genuinely rewarding alternatives. A 2025 study in Nature revealed something even more specific. Dopamine neurons encode not only reward prediction errors, but also what researchers call action prediction errors, signals related to the repetition of past movements, independent of whether those movements produced any reward. This suggests that the habitual, repetitive quality of behaviors may be tracked by a separate teaching signal from the value-based one. Habits feel automatic because their repetition is monitored by its own specialized mechanism. But that mechanism can also be updated through repetition alone, even without conscious reward. Think about what that means. You can begin to overwrite an old habit simply by repeatedly performing a new behavior, even before that new behavior feels rewarding. There's a fragile period in the middle of any genuine change. The old reward circuit has lost some of its pull, but the new one hasn't fully taken hold. The old dopamine predictions are fading, but the new predictions haven't stabilized. Neither pattern generates a strong signal. Everything feels flat. Motivation seems to disappear. This is the window where most people give up. Not because the process isn't working, because the absence of strong dopamine signals from either direction feels like nothing is happening. But something is happening. The prediction errors are accumulating. The old synapses are weakening. The new synapses are strengthening. And every night, the brain's nightly audit proportionally downscales everything, letting the weakened old patterns fall closer to the pruning threshold while preserving the stronger new ones. Stay in that flat middle long enough, and a quiet shift occurs. The new pattern begins to generate its own reliable dopamine signal. The prediction errors stabilize. The basal ganglia starts encoding the new behavior as a default routine. And the old pattern, its synapses weakened by disuse and nightly pruning, becomes like a forest path that no one walks anymore. Dr. Kanojia describes a finding that reveals something unexpected about the dopamine system. The brain produces a reward for moral punishment. You get a neurochemical hit from seeing someone punished who you believe deserved it. Even righteous anger, even the satisfaction of justice, operates through the same reward circuit as any other craving. The brain doesn't distinguish between the dopamine of chocolate and the dopamine of vindication. This means even patterns you think of as virtuous, your sense of moral outrage, your need to be right, your drive to punish wrongdoers, may be operating, at least partially, as dopamine habits. The feeling of righteousness is itself rewarding, and the brain will automate any behavior that reliably produces a reward. Something to sit with. The next group of observations examines whether the brain's capacity for this kind of renovation diminishes with age, and what the latest research reveals about recovering plasticity that was thought to be permanently lost. For decades, the dominant view in neuroscience held that the brain's ability to rewire itself declined sharply after childhood. The critical periods closed. The neural clay hardened. Whatever patterns you carried into adulthood were, for the most part, the patterns you kept. That view doesn't hold up anymore. Dr. Tony Wiscore, a professor of neurology at Stanford University, led the research that first showed something remarkable about aging brains. In 2014, His lab published a study in Nature Medicine demonstrating that exposing aged mice to factors present in young blood plasma improved synaptic plasticity, increased the density of dendritic spines, the tiny protrusions where neurons receive incoming signals, and restored cognitive function on learning and memory tests. Old brains, given the right molecular signals, could behave young again. That initial discovery was striking enough, but what came next was even more compelling. In August 2023, three independent research groups published simultaneously in Nature Family journals. They had been working separately, in different labs, asking different questions, using different experimental methods, and they all converged on the same molecule: platelet factor 4, a protein released by blood platelets. Tara Walker's team at the University of Queensland had been screening the blood of exercising mice to find what made their brains healthier. Platelet factor 4 was among the factors that rose most during exercise. When they injected this molecule into non-exercising old mice, every third day for 24 days, the old mice performed almost like young mice on learning and memory tests. New neurons were being generated in the hippocampus. Walker described the result. The old mice weren't quite back to young mouse levels, but almost. A second team at UCSF found that young blood platelets calm the brain's immune cells, the microglia, reducing the chronic neuroinflammation that builds up over a lifetime. Platelet factor 4 was the most abundant protein in the active fraction, and it worked not by crossing the blood-brain barrier directly, but by calming the peripheral immune system, which then signaled the brain to stand down from its inflammatory posture. One researcher described the effect in simple terms: it seemed to make the microglia happier. A third team, also at UCSF, discovered that the longevity factor clotho activates platelets to release platelet factor 4, which then acts directly on synaptic plasticity. The molecule improved brain function in both young and old mice. Three labs, different starting points, same molecule. In January 2026, Wiscore's lab published another study in Nature, this time revealing what they call the neuronal aggregome, the collection of proteins that accumulate in aging neurons because they're broken down more slowly. They found that neuronal protein half-life approximately doubles between young and old mice, and that 1,726 proteins showed increased aggregation with age. Among these, 274 neuronal proteins accumulated in microglia, with synaptic proteins being heavily represented. The implication: part of aging involves the brain's immune cells consuming synapses that can no longer maintain their protein structures. A chain from impaired protein maintenance to protein buildup to synapse vulnerability to microglial consumption of those synapses to cognitive decline. But the chain runs both directions. Exercise, molecular interventions, and reducing chronic inflammation can push it back. Stem cells in the brain can be reactivated. Inflammatory signals can be dampened. Neural activity and memory function can improve. What does this mean for unlearning? The neuroplasticity required to release old patterns and build new ones is not simply a privilege of young brains. It's a recoverable capacity. The ability to change is not locked behind an age gate. It can be maintained, supported, and in some cases restored, even in brains that have accumulated decades of wear. Your brain at 40, at 55, at 68, it is still capable of renovation. The renovation may proceed more slowly. The molecular environment may need more support, but the fundamental machinery for change is still present, still functional, still waiting to be engaged. These observations about plasticity across the lifespan bring us to the practical question: what actually works? If the brain is capable of releasing old patterns at any age, what are the practices and principles that support the process? The first tool is the simplest one: awareness. Simply noticing a pattern without trying to change it, without judging it, without fighting it, begins to weaken its automatic quality. This feels counterintuitive. You'd think change requires action, effort, doing something, but the first action is observation. When you notice a habitual response as it's happening, when you see it clearly, name it, recognize what triggered it, you shift the behavior from the basal ganglia's automated processing back to the prefrontal cortex's conscious awareness, even for a moment. And that momentary shift creates a gap between stimulus and response that wasn't there before. This is exactly why the attachment style finding is so striking. Huberman's work suggests that simply knowing attachment styles exist, understanding that their patterns formed in childhood, that they're malleable, that they influence but don't determine adult relationships, begins to shift them. Knowledge itself is an intervention. Not because knowledge rewires the synapses directly, but because it changes the perception. And when perception changes, the default mode network updates the narrative. And when the narrative updates, the downstream behaviors begin to loosen. The second tool is cognitive reframing, changing the story the brain tells about a stimulus. This isn't positive thinking. It's not pretending that a difficult situation is pleasant. It's looking at the same situation from a different angle and noticing something genuinely true that you hadn't registered before. When your brain perceives criticism as a threat, it fires a stress response. Cortisol rises, the amygdala activates, the prefrontal cortex partially disengages. But when that same criticism is perceived as useful information, feedback that might help you improve, a data point rather than an attack, the stress response is muted. Not because you suppressed it, because the brain processed the input differently at the perceptual level before the stress response even had a chance to fire. The criticism didn't change. Your perception of it did, and perception sits upstream of everything. The third tool involves what psychologists call exposure and extinction. When you face a fear in safe conditions, repeatedly, gradually, without the feared consequence actually occurring, the nervous system learns a new response. Research suggests the old fear memory may never fully erase, but a new memory forms alongside it. A memory that says, "This situation is safe." And with enough repetition, the new memory becomes the default response that fires first. This is what happens in gradual exposure therapy for phobias. The old circuit is still there, somewhere in the network, but a new, competing circuit has been built on top of it. And because the new circuit has been reinforced more recently and more frequently, it fires first. The fourth principle might be the most paradoxical of all. Fighting a pattern strengthens it. Every time you engage with a habit, even to resist it, you activate the neural circuit that encodes it. You're reinforcing the very pathway you're trying to weaken. This is why "don't think about a white bear" makes you think about a white bear. Suppression is activation. The circuits don't distinguish between wanting to fire and being forced not to fire. Either way, they fire. The alternative is observation without engagement, watching the urge show up, noting it, and then not fighting it, not suppressing it, not engaging with it at all, just allowing it to be there while you do something else. Each time you do this, the urge fires without receiving its expected reinforcement. The prediction error signal registers. Expected reward didn't arrive. The synapse weakens slightly. And that night, during the brain's nightly downscaling, it weakens a little more. The fifth principle is accumulation. Small, repeated shifts compound over time. You don't need a dramatic breakthrough moment. You need 100 quiet adjustments. 1,000. The nervous system's default migrates gradually to a new resting state, not through force, but through the slow, steady pressure of alternative experience. Like a river doesn't punch through rock in a single moment. It flows over the same stone day after day, decade after decade, century after century. And one day the stone is smooth. One day the channel has shifted to a path it wasn't following before. Not because the river used force, because it was persistent, because it kept showing up. The final group of observations widens the view, looking at unlearning not as a single event or a project with a deadline, but as something the brain does continuously across an entire lifetime, quietly, without announcement, without asking for credit. Your identity is itself a pattern. It is the default mode network's most practiced narrative. The story you tell about who you are, assembled from selectively recalled memories and emotionally weighted interpretations, reinforced by the behaviors that story generates, which in turn produce the experiences that seem to confirm the story. It's circular, but circles can be widened. The patterns you carried at 20 are not the patterns you carry at 40, not necessarily because you fought them, but because you lived. New experiences entered the system. New prediction errors updated old expectations. Relationships formed that challenged old attachment templates. Environments shifted, channeling genetic predispositions into new valleys on the Waddington terrain. What looks like sudden change, the person who quits a destructive habit after decades, the person who leaves a career that never fit, the person who finally sets a boundary they were afraid to set for 20 years, is often not sudden at all. It's the visible moment when years of quiet erosion reach a tipping point. The synapses encoding the old pattern have been weakening for a long time. The narrative in the default mode network has been slowly revising. The dopamine predictions have been gradually updating. And one day the balance tips, not with a crash, with a quiet click. Sometimes change announces itself. Most of the time it doesn't. Dr. Hardin's work carries a message that runs through everything we've discussed tonight. The desire to better yourself, no matter what your genes are, and to better the world. That desire is not naive. It's neurobiologically supported. Your genes channel behavior, yes, but your experiences modulate those channels. Your awareness allows you to see the channels for what they are. And your brain, every single night, runs the biological process that weakens what you didn't reinforce that day. The nervous system is a living document. It's always being edited. The cells on your tongue are replaced every 2 weeks. The synapses in your cortex are proportionally downscaled every night. The default mode network revises its narrative with every new experience that contradicts the old story. The dopamine system recalibrates its predictions with every outcome that differs from what it expected. You're not the same neural network you were 5 years ago, not the same web of predictions, not the same collection of synaptic strengths. The change happened too gradually to notice, like watching the hour hand of a clock, but it moved. And it's still moving right now. The brain doesn't require extraordinary effort to release old patterns. It requires time, alternative experience, and the absence of reinforcement. The nervous system was built to update, built to prune, built to revise. The old path through the forest grows over, not because someone hacked the bushes away with a machete, but because they walked a different route, night after night, until the grass returned and the roots spread across the bare soil, and the old path was no longer visible at all. Unlearning is not loss, it's not destruction. It's the brain making room, space for new connections, new predictions, new chapters in the story of who you are and who you might still become. And here is perhaps the most striking connection of tonight's journey. Your tongue was born hating bitter and loving sweet. This is hardwired into molecular architecture that predates human civilization by hundreds of millions of years. An infant tasting coffee would gag and recoil, the ancient rejection program executing exactly as designed. Yet right now, across the world, millions of people are looking forward to their morning coffee. The same mechanism that rewired their taste preferences, learned associations layering positive value on top of a hardwired negative signal, is available for every pattern in your life. Dr. Zuker's phrase is worth resting with. Predetermined hardwired doesn't mean it's not modulated by learning or experience. That single sentence holds the entire science of unlearning. The predisposition is real, the biology is real, the wiring is real, and it can be rewritten. Imagine every negative pattern as a path through a forest. Each time you walk a different route, the old path grows over just slightly. Grass returns at the edges. A root stretches across the bare soil. Leaves fall and settle without being kicked aside by passing feet. Given enough time, enough nights of synaptic downscaling, enough days of alternative experience, enough dopamine prediction errors gently updating old expectations, you would never know the old path had been there at all. The brain's default tendencies are not permanent. They are the nervous system's best guess, based on the data available at the time, the childhood experiences, the genetic nudges, the environmental reinforcements, the reward histories. But guesses can be updated. Predictions can be revised. The nervous system was designed for revision. Willpower is for the transition. It's the prefrontal cortex holding the line while new experiences accumulate, while new dopamine predictions form, while the basal ganglia begins encoding the new pattern as its default. Once the tendency itself changes, once the new pattern has been automated and the old one pruned, effort dissolves on its own. Even the deepest patterns bend. Childhood attachment templates formed before language, recycled into adult love, shift when new relationships provide new data, and when awareness illuminates the pattern for what it is. Genetic predispositions, real and measurable, can be overridden when environments change the terrain through which those predispositions roll. Hardwired sensory responses, the most ancient circuits in the human body, get rewritten when new associations provide sufficient reward. All of this happens through the same fundamental process. The nervous system tracks predictions. When reality differs from prediction, it updates. When a pattern goes unreinforced, its synapses weaken. When rest arrives, the brain's nightly audit weakens them more. Given enough time, they fall below the threshold. They are pruned. Not fought, not suppressed, not conquered by force. Pruned by a system that was built for exactly this purpose. Right now, as you listen to these words, as your breathing slows and your thoughts begin to soften at the edges, your brain is preparing for its nightly work. The slow waves will come. The synapses will be proportionally downscaled. The patterns you reinforced today will be preserved. The patterns you didn't practice will weaken. This is not something you need to do. It's something that happens on its own, every night, quietly, without your awareness or your permission. The brain continues its quiet work. Old patterns soften, new pathways deepen. Somewhere in the space between waking and rest, the nervous system lets go of what it no longer needs. A synapse that once fired urgently goes silent. A story the default mode network told for years gets gently revised. A prediction error that once drove behavior settles into the flat line of a lesson already absorbed. The cells on your tongue are being replaced. The synapses in your cortex are being pruned. The narrative of who you are is being edited, even now, in ways too subtle for you to notice. You are not fixed. You were never fixed. You are a pattern, learning to become a different pattern. And that isn't a failure of permanence. That is the design. The nervous system doesn't hold on to what it no longer needs. It lets go, quietly, slowly. The way a river lets go of the shape of its old banks as it carves, over centuries, a new and gentler course through stone. Stars form, neurons fire, connections strengthen and weaken according to the oldest rhythm in biology, the rhythm of use and disuse, of reinforcement and pruning, of prediction and quiet revision. And somewhere within this vast, slow motion, rest gently arrives. Sweet dreams, and we will see you next time on Bedtime Science.